Talk of the morning session from Tamás Schwarcz. He will be talking about reconfiguration of basis pairs in regular matroids.
Yeah, thank you very much for this opportunity. So today I will present our joint work with my PhD supervisor, Kristóf Bérczy, and with Bence Matroids, who was an undergraduate student in Budapest at the time we did most of this research. So we'll talk about basis pairs, which are just ordered pairs formed by basis of a matroid. And if we have a basis pair A1, A2, then we can get to other basis pairs by symmetric exchanges. The strong exchange or symmetric exchange property implies that for any element in A1 minus A2, we get an element such that we can exchange such that both the resulting sets are basis. So for any basis pair, we can get to some other basis pair. So it's a natural question that what are the basis pairs that are reachable by sequences of symmetric exchanges from a given basis pair. And the symmetry exchange doesn't change the intersection or the union of the two bases. And it's a conjecture by White from the 80s that this is the only necessary condition. So if the intersections and the unions are the same, then there is always a sequence transforming one basis pair to another. Here we can contract the intersections and delete everything which is not in the union. So we can think about pairs of disjoint bases of a matroid such that the ground set is the union of the two bases. So we have partitions of the ground set into two bases, and the conjecture said that we can get from any partition to any other partition by doing a sequence of symmetry exchanges. Let's look at an example. So we have the graphic matroid of K4, and we are given two basis pairs. The bases are denoted by the colors. Then we can get a sequence between these two. But even in this case, it's not entirely trivial, because in the first step, we need to use either the edge AD or BC, so something which has good color originally. So in the first step, we cannot get closer to the final basis pair seemingly, but if we do one exchange, then after that we can finish and get this exchange of length 3, despite the A1 minus B1 had just size 2. But in this example, 3 exchanges are needed. So one reason why this conjecture is difficult is that we can keep on doing exchanges, but it's not clear what quantity improves if we do these exchanges. How do we get closer to the final basis pair? There is a very related conjecture which is even earlier than this. It was a question by Gabo that in the special case when the second basis pair is just the reversed first one, then there is always a sequence of lengths r where r is the rank of the matroid. So in this case, we can decrease the difference in each step. Equivalently, if you like cyclic orderings, these are completely different cyclic orderings, but still, this is equivalent to saying that there is a cyclic ordering of the ground set of the matroid, such that these given bases A1 and A2 form intervals of length r, and any other interval of length r is also a basis. So this will be a sequence of length r that goes from first basis pair to the second. Okay, so we worked on these two conjectures, but to give context, I will mention some other algebraic and geometric conjectures that are really related to this. So White came up with these conjectures and variations on these conjectures by studying the toric ideal of a matroid. So if we have a matroid, we can consider the polynomial rings where the variables correspond to the basis and where the variables correspond to the elements. And there is a natural homomorphism between the two, where we map a variable corresponding to a basis to the product of the variables corresponding to an element. And if we look at the kernel of this map, then this is called the toric ideal of the matroid. And White conjecture that this toric ideal is generated by these binomials of a special form. So here we multiply variables corresponding to two bases and subtract something which has similar form with a basis pair which is reachable by a symmetric exchange. And if you look at all these elements, the conjecture is that this is a generator of the toric ideal. And to get a conjecture that is similar to the one that we studied, I can show that this is equivalent, that for any set of k bases, you can get to any other set of k bases by symmetry exchanges. whenever the unions are the same as multisets. So the conjecture of Y that we studied corresponds to the k equals 2 k's of this, but we studied ordered pairs, and here these are unordered. But also for this more general conjecture, you can consider this is also a conjecture with ordered k tuples of basis. And to see a connection with the geometric version, there is an even stronger conjecture that these elements not only generate the steric ideal, but form a Gröbner basis. In particular, of the steric ideal, in particular, this would imply that it has a quadratic Gröbner basis. And this conjecture have a nice geometric translation. It is equivalent to that all matroid base polytopes have regular unimodular flag triangulations. And there was a recent breakthrough result by Spencer Bachman and Liu, who showed that at least there are triangulations satisfying 2 of these 3 properties. So now it's known that there are regular unimodular triangulations, but this formalized question would also require that they are flag. Okay, so these are the motivation, one of the many motivations to study these conjectures that we studied. So let's get back to this basis pair setting. So what is known about these conjectures for special matroid classes? For example, they hold for strongly base orderable matroids. We have already seen some today. For example, gammoids are strongly base orderable. They also hold for sparse paving matroids. So if almost all matroids are sparse paving, then they hold for almost all matroids. And with Christoph, we generalize this to split matroids. So a superclass of sparse paving matroids that includes, for example, paving matroids that we have heard about today from Benjamin. When he talked about elementary split matroids, so actually that's why we studied elementary split matroids with Christoph, because we wanted to prove these conjectures for split matroids. But more relevant to today's talk, they hold for graphic matroids. There are lots of independent equivalent proofs in the literature, in several papers. So how to prove this for graphic matrices? I will tell the main idea because it's important for our proof. The main idea is that we have a partition of the graph into 2 spanning trees. So if the graph has n vertices, then it has 2n minus 2 edges, which implies that there is a vertex of degree less than 4, which is the union of 2 spanning trees, so a vertex of degree 2 or 3. And in both cases, we can apply some induction. So if we have a vertex of degree 2, then we just delete this, apply induction to the smaller graph, and get a sequence in the original graph. And if there is a vertex of degree 3, then 2 edges belong to the same spanning tree, and we connect the end vertices of this and delete the vertex. Again, we get a smaller graph, which is still the union of 2 spanning trees. And it's not very difficult to see that how to get a sequence in the original graph from a sequence in this smaller graph. So that's the main idea of the proof for graphic matroids. And for both of these conjectures, the conjecture for a matroid is equivalent to the conjecture for its dual. So this also implies that the conjecture holds for co-graphic matroids. But I also wanted to mention that this graphic matroid proof shows a sequence of lengths, the square of the rank for White's conjecture, and also shows Gabow's conjecture. So these conjectures were known to hold for graphic and co-graphic matroids for a long time. It was also asked in at least 2 papers whether someone can show them for regular matroids, and our result is that we showed that these 2 conjectures do hold for regular matroids. In particular, for White's conjecture, our sequence that our proof gives has lengths 2 times the square of the rank. So we also get a bound on the distance, which is slightly worse than what the proof gives for graphic matroids. So something is true for graphic and co-graphic matroids, so how to prove it for regular matroids? The natural idea is that we know that regular matroids can be built from these building blocks. more precisely, a regular matrix can be obtained from graphic matrices, co-graphic matrices, a specific matrix called R10, using matrix operations 1, 2, and 3 sums. So R10 here is really just a specific matrix, this binary matrix on elements. So it's, for these conjectures, it's not difficult to check that they hold. So our only task would be to use 1, 2, and 3 sums. So what are these? For graphs, you can define it using these cliques. So you have two graphs such that they intersect on a common clique on k vertices. And then you delete this clique. And this is the k sum of this graph for k equals 1, 2, and 3. So for k equals 1, they just share a vertex. So in matrix terms, this is just a direct sum. So one sum is easy to define also for matrices. Two sum is also not difficult to define for general matrices. For example, we did basis family. And for binary matrices, one can also define 3 sums. Someone wants a definition. The cycles, which are in a binary matrix, which are the cells that can be partitioned into circuits. So the cycles of a 3 sum or a k sum are the symmetric differences of the cycles of the two matrices. So these are the matrix operations that we need to use. So natural proof strategy is to show that the class of matrices that satisfy White or Gabor's conjecture is closed under 1, 2, and 3 sums. For example, for 1 sums or direct sums, it is quite easy because you can just apply the exchange sequences that you get from the two components independently, and then merge together. This gives an exchange sequence for the whole matrix. So why is this result non-trivial then? It's because of 3 sums. Because for 3 sums, it's quite complicated how to merge exchange sequences that we get. So here is an example with a graphic matrix. So here, this is this triangle V1, V2, V3, along which we perform the 3 sum to get the graphic matrix. In the original, we had a basis pair. When you look at the parts of these 3 sums, it's currently these are not bases, but you can add back some edges of the triangles to get bases there. So you have some freedom how to choose, but the natural idea would be to add back some of these edges. For example, we added like these, then we get basis pairs in these smaller matrices, and then by induction on both sides, we could get exchange sequences and try to merge those. But this approach, we couldn't make it work, because for example, if we just consider arbitrary exchange sequences, for example, for Gabor's conjecture, let's say these are the first 2 exchanges that the induction gives, then these are not compatible with each other, so we cannot glue them together to get basis pairs in the original matrix. For example, for what we get on the left-hand side in this example, there is no partition of the right-hand side, such that what we get is a basis pair in the original matrix. So it seemed complicated to solve the case of 3 sums in general, and we didn't even manage to do it. So to prove for regular matrix, we required some new ideas. So the idea was that we don't have to solve the general case of this 3 sum that we couldn't manage. But first, we applied many reductions to the problem, because so we could solve direct sums and 2 sums by merging these exchange sequences, and we found further reductions. For example, if there is a set whose size is twice its rank, then by induction we can reduce the problem to a smaller one. And here the most important reduction that we found is that we can assume that the matrix doesn't contain a circuit or co-circuit of rank at most 3. So if we have a co-circuit of not rank size, if you have a co-circuit of size 2 or 3, then the same proof that worked for graphic matrices by removing these vertices works in this case. So for example, if you have a cocircuit of size 3, then we contract one of its elements, delete one, get a smaller matrix that is still the union of two bases. And if we have a sequence for the smaller matrix, that were to give a sequence for the larger matrix. So these reductions work for any matrix if you want to prove these two conjectures. And for regular matrices, we used slight generalizations of Seymour decomposition theorem. So if a matrix is 3 connected, we didn't only use that it's the 3 sum of two smaller regular matrices, but we use that it's either a 3 sum with a graphic matrix or with a co-graphic matrix, where this gluing is quite special. That is, this triangle in the co-graphic matrix corresponds to a cut of the graph that belongs to a vertex. And if we have this special case, then if we take the dual, then we get back to the first case when we have a graphic matrix. So by using this slight generalization of the decomposition, we could reduce to the case when we have only a 3 sum with a graphic matrix. And if we have those reductions, then we could even show that the only case that we are left with is that if we have a 3 sum with a graphic matrix of a 4 regular graph. So here we use that the matrix is the union of two bases and there are no small circuits and co-circuits. So instead of solving 3 sums in general, it is enough to solve 3 sums with graphic matrices of 4 regular graphs. And by using more observations on graph, this is finally that we could solve. So why does it help that we have a graph? Because we can use some stronger statements on the graphic part. So how we prove these conjectures is that we found some stronger conjectures for graphic matrices, and we use those on this side of the 3 sum to show the conjectures for the original matrix. So for example, for White's conjecture, we show that there is an exchange sequence that does not use a fixed element, that doesn't have to change color. And then when showing for the original matrix, then we choose this element to be an element of this triangle in the gluing, and this helps us to control these sequences. And another thing we used about graphs, that in this special case when reductions apply and we have a 4 regular graph, we found some nice partition into forests of this graph when we did a triangle. And with these ideas, we could finally apply this proof that we have this 3 sum, apply induction on the regular part, and use this stronger statement on the graphic part. So this is how we prove these conjectures for regular matrices. And today we have algorithmic Friday, so everything works in polynomial time for finding these exchange sequences. And yes, and our algorithm gave an exchange sequence whose length is quadratic in the rank of the matrix. Okay, so to conclude, here are some remarks. So actually, we proved this conjecture for a superclass of regular matrices, but regular matrices are more well known. But the same proof worked for the so-called max-flow-min-cut matrices, because there is also a structural theorem for them that they can be obtained from regular matrices and copies of the Fano matrix by 1 and 2 sums, and everything works also for this class. So some open problems. So there is this version of White's conjecture that is related to this is a stronger conjecture than the one motivated by the theoretic ideas, that for ordered sequences of k tuples, whether the same is true. And this is a statement that is known to hold for graphic matrices by a proof of Blasziak, so it might be possible to generalize to regular matrices, but we haven't figured it out yet how. And there is also an open problem for graphic matrices, because that proof doesn't give an exchange sequence of polynomial lengths. So it is not clear whether, it's not only not clear that whether there is a polynomial algorithm for finding a sequence, but even whether there is a sequence of polynomial lengths, because in this, Blasziak's construction gives a sequence of exponential lengths. But at least with exponential lengths, it might be possible that one can show this conjecture for regular matroids. Another open problem is that so for these graphic matrices or regular matrices, the best upper bound on we have on these distances of basis pairs is quadratic in the rank, but we know about no example where more than rank many exchanges might be needed. And we found it in a paper that Amidon asked whether it is true that there is always a sequence with rank many exchanges. But we thought a bit about it for graphs, but it's entirely not clear why would it hold for graphs. It's a very interesting open problem. Because if this conjecture is true, then it would generalize both this Weiss conjecture for basis pairs and Gabos conjecture. Okay. But for this stronger conjecture, at least we could, our proof for split matroids also showed this conjecture. So this is some evidence that at least for split matroids, this conjecture holds. Okay, thank you for your attention. And here's the paper if someone wants to read.
Thank you, Tamás. Any questions? Oh, all the way in the back.
Does this resolve White's conjecture about the generators of the toric ideal for regular matroids?
Sorry,
You mentioned White had a conjecture about...
yes, this is also open for graphic matroids. I think this lot of...
Yeah, that one.
Yes.
So your argument does not resolve that conjecture as well?
So here we have, this is for any k.
Oh,
and we
any
haven't
k.
showed that yet for
Yeah,
any
I
k,
see.
but if we could show this for any k with order sequences, that would be stronger than this with the toric ideals.
I see. Okay, thanks.
Any other questions? All right, if not, let's thank Tamás again.